Welcome to YMT211, Discrete Mathematics. This is Chapter 1, Fundamental Principles of Counting. So we'll speak about counting in a basic sense. We'll explain about its rules, and we will link these rules or the basic rules and elaborate how we use them as foundation for other laws and actually advanced rules that we will use now and in another chapter for advanced counting later on. For this chapter, we will try to make our discussion restricted to the principal policies and rules, and then we will elaborate further. Why do we need to study counting? What is it anyway? Actually, counting is exactly finding the number of possibilities or the number of outcomes or possible outcomes. Possible outcomes of what? Of everything. Literally everything. So if you are studying software engineering, you study different courses. One of them is data structure. For example, you may need to calculate the number of steps the algorithm takes. And in that case, you can determine the complexity of the algorithm. That's one of the applications. If you are thinking about the coding theory, there is an application for counting. The probabilities also. Statistics also. So that is why we have counting involved in many disciplines in our own field. That's why we study it, okay? And that's why we give it not only one chapter, actually two chapters. One of them, this is the basic concept. We address the basic concepts, not only concept. And then we have an advanced counting chapter that will be studied around the 8th week or so. Until then, we will just explain those and restrict our discussion to them. Okay, the first rule that we will elaborate and explain, and I am sure you guys are familiar with it, you studied it in high school, I checked already, but let's just revise what you studied and put it in an academic template so that you use it based on a bit advanced way or a bit higher in an understanding. That's exactly what refers to an academic sense. All right, let's say we have two different tasks or two different procedures. They may be more than two. Let's just for simplicity discuss two at the beginning. Two different procedures, and these procedures are distinguished. They cannot be done at the same time. So they have no related outcomes that affect one another. So they are not done simultaneously or simultaneously. So it's up to you to do the first one or the second one first. So they are not done together. This is a condition. And in that case, if we have a number of possibilities from the first procedure, let's say m ways. So we can do the first procedure in m ways and the second procedure in n ways. Then the total number of possibilities or ways that we can do the both procedures is exactly the summation of the outcomes from the first procedure plus the outcomes of or the possibilities of the second procedure. And that's what we refer to by procedure 1 or procedure 2, or the possibilities of procedure 1 plus the possibilities of procedure 2. Okay, we can generalize it to as many procedures as possible. Now, the idea is they must not be done simultaneously, they cannot be performed at the same time, and that's exactly the condition. All right. So let's just take an example. Let's say you have the choice, when you go to a restaurant, you have a choice of 18 dinner sets with meat and 10 sets with fish. So now look, these two are not mixed. 18 dinner sets with meat and 10 sets with fish. They are not mixed. So different procedures, the outcomes, 18 here, choices we have, 10 choices, they are not mixed. They are not done in simultaneous way. They have some distinguished characteristic. That's why if you want to choose from these 18 dinner sets, you have 18 choices. And the 10 sets, you have 10 choices. So how many choices do you have from all? You just sum them up. So the outcomes from the first procedure, it's possible to choose between 18, so whatever any of the 18, so you have 18 choices, plus whatever, any one from the 10 choices, that's 28 choices in total, okay? Let's take another example. Let's say as a student you have the right to borrow 3 science books, whatever science and technology, let's say, from the library, and 2 novels, and 4 literature books. So, first task, you can borrow 3 science books. They are not as the stream of novels. They are also not as a stream of literature, and the novels cannot, let's say, cannot be also attached to literature. In that case, we have 3 separate tasks, and their outcomes cannot be done simultaneously, and they are not, cannot be achieved simultaneously. So this one is separate, and this one is separate, and this one is separate. So they are all recognized by certain characteristic, and for that, in how many choices or how many choices do the student have at any time? So I have 3 for the science, I have 2 for the novels, and I have 4 for the literature. Just sum them up, and that's exactly the total. 3 plus 2 plus 4, that's 9 choices at any time. Okay. At the rule of product, so we took the rule of sum. 2 distinguished procedures cannot be done at the same time or simultaneously. In that case, we add the possibilities or the outcomes. But assume that we can have a procedure that can be broken down in 2-second procedure. Okay, first and second procedure. So basically we have a task which is actually combined. We have first part and second part, first stage and second stage. So the first stage we have, let's say, m possibilities, and the second stage has n possibilities. Then the total possible outcomes will be m times n. And that is what we refer to by the rule of product. So in that case, the procedure is done simultaneously, but with different stages. We don't have distinguished characteristics in this case, we just have separate stages, but of the same procedure. Remember that here a procedure can be broken down. So the procedure here is 1, but we can break it down to stages. Multiple stages are possible, not just 1 or 2 stages. It could be more than that. Okay, and in that case we say m and n. It is exactly one procedure broken down into stages. Here in this case, just basic sense, 2 stages, m and n possibilities, multiply them, m times n, that's the total outcome. And let's take some examples. These are quick examples. We will have a separate tutorial later on, not now, okay, in another separate video. Let's say we have 31 flavors of ice cream and 4 sizes. Now look, 31 flavors. For each flavor, we have 4 sizes. So it's not 31 plus 4. No, for each of the 31, so each flavor has 4 sizes of serving. And in that case, we can break the procedure of choosing, okay, the order that we make in 2 stages. The first one is choosing between the flavors and then choosing between the sizes. So now you can make a sense of the idea. All right. So how many different orders of ice cream are there, or how many different orders of the ice cream are there? Of course, we have 31 flavors, so we can make 31 orders for the flavor only. But if we break the procedure of order to 31 for the flavor and then 4 for the sizes, for each of the 31 we have 4. So 31 times 4 multiplied by 4, and that is the rule of product. Why? Each and every one of the flavor has 4 serving sizes, and that's what composes the stages of the selection. All right, let's take another example so that the idea becomes a bit more clear. How many possible outfit combination, and this is very good actually for you. You guys maybe try to make a nice outfit with some matching color and maybe design. Let's say, in how many possible outfit combination can you form if you have 3 shirts, 3 pairs of jeans, and 4 pairs of shoes? So now look, we do not have separate tasks here. What we have is it one task that we compose an outfit, but this outfit is by itself composed of 3 selection stages. Before we took 2 selection stages here, 31 flavors and 4 sizes. Here we have 4 shirts, 3 pairs of jeans, and 4 pairs of shoes. So for the 4 shirts, we may use any of the 3 pairs of jeans and any of the 4 pairs of shoes. Okay, it's possible. These are the possibilities. It doesn't matter if they fit or not. Now we are not speaking about the colors and the matching. How many ways are possible outfit? So we multiply the first stage times the second stage times the third stage. That composes all possibilities. Now which one suits you? That is actually determined by you. You can check all the possibilities in front of the mirror and see which one is the best, but that's exhausting. So 48 different possibilities will take a lot of time from you to check all of them, but that we just say the counting here, total. So the total of all of these possibilities. Now again, why it is not the rule of sum? These are not separate. The choice of shirts is actually followed by jeans, or maybe the jeans followed by shirts, because the order here doesn't matter. And the choice of shirts and shoes are also followed by the jeans and so on. So, or vice versa. We may replace the order. The order doesn't matter in this case. Okay? We don't have any distinction that says you should choose this one before that one. Okay. Let's go to another example, and this one has an exception, but I will explain it for the time being. Why? Because it has its own idea that I will explain about it in a while. Let's assume that we have cell phone company, a cell phone operator, whatever operator you think about, and this operator is assigning 10 digits for each user or customer. Of all these 10 digits, the first 3, let's say, used for the company, so they are unique for the company, they don't change. Whatever you say, it depends on wherever the country that you are residing or buying your cell phone from, and the operator as well. So we don't care about the first 3 digits. We go to the next 7 digits. So for the next 7 digits, we may have any possible digit that we have in our decimal system. So we have 7 digits, we can arrange them like this. 7 digits here, I mean only the digits. But for each of the 7 digits, how many possibilities do we have? Now think about the digit, any digit, decimal digit, can be from 0 to 9, right? We can count 0, 1, 2, 3 until 9. That's 10 possibilities. So if you count from 0 to 9, so 0, 1, 2, 3 till 9, these are 10 possibilities. Okay, 10 possibilities, we have 7 of them. So multiply 10 7 times for each of the digits. That's exactly 10 millions possible combinations. So in a country, in crowded countries, if you're using this kind of 7 digits, it may not be enough for the customers. So that's why sometimes they use different identifiers. So that they use more than one identifier. So they double this number, it will be 20 million. Or if they use like 2 digits of identifier, that will make it not double, that will make it much higher than that. Okay? We'll speak about that in a while. But here, why we have these 7 digits, for each digit we can choose one of the 10 possible decimal digits, and that's exactly rule of product. Okay. This one also has an idea, and I would like to explain it now so that later on, when we explain about the permutation, you'll understand what I'm saying now in a better sense. Let's say you guys actually like social media in general. So let's say you use Facebook. Let's say you have 30 friends on Facebook. And let's assume anytime you log in your Facebook account, you get of these 30, 6 online. So of these 30, randomly, every time you log in, you find 6 of the 30 online. Any 6, it doesn't matter. Any of them, it doesn't matter. Okay? So these are randomly generated from the 30. In how many different arrangement of 6 people can show up? So we have 30, the total number of friends that you have, and each time you log in, you get 6 online. Okay, now think about this easily. Let's explain about it in a basic sense. We have 30 friends. Let's say we have 6 of them appear online. I say 1, 2, 3, 4, 5, 6. I arrange them this way. I give friend number 1, number 2, number 3, number 4, number 5, number 6, and they are randomly generated. Okay, each time number 1 is not the same. Okay, it keeps changing. But the first one has how many choices? 30 choices. Why? Because we have 30 friends. So if we say number 1 could be any of the 30, how about number 2? It will not be any of the 30. Why? Because 1 is already assigned. So number 1 took any of the 30. So now we don't have 30. We have 30 minus 1. Okay, so the second one will be any of the 29, or 30 minus 1. How about number 3? Number 3 will be 30 minus 2, because we already covered 2. First one took one of the 30 choices. Second one took one of the 29 choices, or 30 minus 1. The third one will take 30 minus 2, or 28 choices, and so on. So that's exactly a rule of product, but with some exception. 30, the first choice. Second choice, 30 minus 1, of course, multiplied by 30 minus 2, the possible choices, multiplied by 30 minus 3, multiplied by 30 minus 4, multiplied by 30 minus 5 for the all 6 choices or possibilities or friends. That would be a huge number. Okay. Good, actually, I came to this. During my exams, usually I don't care about the final answer. It's not my aim, especially in such cases. We don't care much about that. Okay. So it's enough. It's good enough for us to get up to here, up until here. That's good enough for you. Okay. The rule of division. This is an exception of actually counting. Now imagine that we have, let's say, a task that can be done in n ways. Okay. We have a task that can be done in n ways. Okay. And for each way of these n ways, let's refer to the way, only one way of the n ways. We have n ways, there could be 5, 10, 20, 30, okay? One of them, for each one of them, we have exactly d ways, okay? Of the n ways correspond to that w way. So we have a repetitive procedure here. In that case, the total outcome will be n divided by d. We have less possibilities. I'll give a common example about this. Maybe it's a bit vague now or not clear to you. I'll give an example and I explain why it is. No need to just go through the definition. We will go through the concept by an example. Now look at this. How many different ways are there to seat 4 people around a circular table where 2 seats are considered the same? Now think about the condition. When each person has the same left neighbor and the same right neighbor. Okay, let's realize it in graphical representation. Now this is a circular table. Okay. Now what we have here, we need to seat 4 people. So think about these places. We don't have any reference. There is no. And the question doesn't say there is a reference. So this circular table, if we seat the first person here, okay, or here, or here, or here, it looks to us the same. So how many possibilities? Now for the time being. For the time being, remember, this is, I don't say this is correct. Okay? I just say for the time being. Now for the time being, what I'm going to do is I'll just say I'm placing 1 here. But if I want to place it here, also possible, here also possible, here also possible. So how many choices do I have? 4. Okay, I don't say this is correct. Just follow up with me, no problem. So for the first seat, we have 4 choices. How about the second seat? So if I place it here, I have a possibility of this seat, or this seat, or this seat, so 3. So the first seat we could place anywhere, 4 choices. For the second seat, this is occupied, we have only 3. So if this one and this one are occupied, then we have only 2. So if this one is occupied, then we have only 1 choice. So 4 times 3 times 2 times 1. That's a factorial of the number. Okay? It looks good, but it's not correct. Why? Now I explain to you why it is not correct. Now look. Now this table has no reference. There is no reference. It's a circular table and there is no reference. We don't know if this one is the same point as this, if this one is the same point as this, because there is no reference. It's just a circle. Any point to us, if we are at the center, any point to us looks same. So if I seat the first person here, it is the same to me as it is sitting here, or here, or here. There is no reference. So this makes only one kind of a choice that I have for seating the first person anywhere. So sit the first person anywhere, which is actually sounds to the table or to wherever, because we don't have a reference in this case, like us looking from the screen view exactly to the center of the table. It looks to us the same. Now you may say, but this is closer to me. Yes, but if you take a point somewhere here, it's the same. This one is the same, this one is the same, this one is the same, this one is the same. And in that case, for the first person, we have only one possibility anywhere. Once one person is seated here, or here, or here, or here, then we have a reference. Why we have a reference? This one is seated. We have left and right and opposite. So it can be determined. So we have 3 choices, either left or right or opposite. So if we seat the person opposite, then we have right to this person and left to this person, or right to this person, sorry, left to this person and right to this person. That is how we count. So the first person will take only 1 choice, and then the second person will have 3 choices, and the third person will have only 2 choices, and the last person, or the fourth person, will have only 1 choice, the last or the remaining choice. And that's the procedure. I explained it in details here. If you couldn't catch the idea of what I said, I believe it's clear actually. Okay. So what would it make? So we said what I said earlier, 4 times 3 times 2 times 1 sounds correct, but it is incorrect. Why? The first person to be seated has only 1 choice. So that makes 1 times 3 times 2 times 1. That's exactly 4 minus 1 factorial. So not the factorial of 4. Or if you want to apply the rule of division, that is the factorial of 4, or 4 factorial divided by their numbers, 4. Why? Because we have 4 possibilities for the same seat repeated. Okay, and that is exactly the idea. So the rule of division in this case allows us to exclude the repetitive ways that can be excluded from whatever we have as repetitive here. The first choice or the first seat can be anywhere of these 4, so we exclude them, we divide them. Okay, that makes it only 6 possible ways. In this case, 3 times 2 times 1, that is the factorial of 3, or the factorial of, open parentheses, 4 minus 1. Okay, 4 minus 1 factorial. Okay. Let's take another topic which is relevant actually, the permutation. The permutation you guys studied in high school. I know, I checked your syllabus of high school. And I know you have an idea about it, but let's just revise what you took and take you to a bit higher level to the academic side. Permutation actually is the counting of linear arrangement where the order matters, Order matters means what? Let's say, we usually give this example, which is the simplest. When we say ABC, it's not the same as BAC. Order matters. So ABC is not BAC, or if you say 1, 2, 3 is not like 3, 2, 1. Order matters. So we have a number of counting here called permutation, and we usually refer to permutation of what? Permutation of a subset from a whole set. Okay, so set R taken from set N. I'll explain about that in short while. So in this case, let's just get back to these three. Now, how many letters we have here? The letters we have A, B, C. These are 1, 2, 3 letters. Okay, so if we want to make them in different arrangements, and how many arrangements can we make them based on the permutation here, where the order matters. Okay, order matters. That means BAC is not as ABC. Okay, in that case, we have 3 letters, so 3 for the first choice, 2 for the second choice, and 1 for the third choice. That's 3 times 2 times 1, and that's exactly the factorial of 3. So n times n minus 1 times n minus 2, or whatever here in this case. If we refer to n by 3, that's 3 times 3 minus 1, that's 2, 3 minus 2, that's 1. That's the factorial of n, factorial of 3. Okay. Actually, counting in this way is easy. But if we say we have selections, then we have R of taken of n. Usually questions come from that. So arrangement like this and straightforward is easy. Usually we don't say that. We have selecting 3 items of a set of 5 where the order matters. If the order matters, then we can select in a permutation order. If the order doesn't matter, in that case we have another rule. We call it combination. We will set it after a while. So the whole set is 5, and we have a subset. We call it the selection criteria, or the selected items, R. So we have a permutation of R of n. So permutation R of n, or R taken from n, or R taken out of n. So number of choices. In this case, if we are selecting 3 out of 5, we have 5 choices for the first item, then 4 choices for the second item, 3 choices for the third item, and that makes it 5 times 4 times 3. And this one has a specific rule. We will study it in a while. It has also its own derivation. I don't usually ask about the derivations in the exam. However, if you are interested, you can check, you can refer to your textbook and check how it is derived and how we can get the rule of it. If you want to go through this way without memorizing anything, that's fine. So you have the whole permutation, the whole set for the first selection of the permutation, then the full set minus 1 for the second one, and so on and so on. Remember the earlier the example I gave about Facebook. We have 30 friends, 29 multiplied by 29 multiplied by 28, and so on. This is exactly the concept of selecting 6 of 30. Okay, I said I will link it in a short while. Okay, so in order for us to put it in a mathematical formula, not just to make it randomly like now, we make it in a mathematical formula. We can use this way, the permutation of R taken from n. Okay, that is the factorial of n, or the n factorial divided by n minus R factorial. So we exclude R from the whole set, and we divide the whole, the factorial of the whole possibilities of the bigger set, or the full set, from the full set minus the subset in terms of the factorial. This is the rule. If you are not a big fan of memorizing or remembering, then you can just go for this, but make sure that you don't make a mistake while following the step. It's really not difficult to train yourself to remember it and memorize it. Okay, so let's take just a direct example. Cold Stone Creamery has a total of 31 different flavors. Again, we have 31 different flavors. They are running a special where you can get 3 scoops for the price of 1. Well, we have some idea here. How many ways can you order 3 different flavored scoops? Now, we have 31 flavors. Okay, we can choose any of these flavors. Okay, but the idea here is not just choosing any of the flavors, because there is an offer where you can get 3 scoops for the price of 1. So we are choosing 3 of what? Of the whole set. So we have a subset here, the number of choices we need to make, of all possibilities of the whole set. So the permutation of 3 of 31, or taken of 31. So that's 31 factorial divided by 31 minus 3 all factorial. Or if you like, you can say 31 multiplied by 31 minus 1, that's 30 multiplied by 29, that's 30 minus 1. So that's the idea. I don't care usually about the final value. Maybe we will change the policy, but for the timing I really don't care about it. I personally do not have any interest in the final answer here. I just need this application. That's enough for me. Okay, and this is the idea. Now here the choices, actually the order doesn't matter to us. There is no any relation of how the order is done. We can just choose, and the selection is actually going back to the permutation. All right. Now we may have repetition in the permutation, and if we have the repetition, it goes back to the rule of division. Why? Because we have again, for each n way, for each of the n way, we have w way done in d ways, total ways. We need to divide by d, and the number of their repetition, if they are repeated more than 1 time, we need to take the factorial in the division. So let's just take a very easy and straightforward example. In how many ways can all of the letters in the word assassination can be arranged? Now look at the word assassination is composed of 13 letters, right? Count them: 3 plus 3 plus 3 plus 3 plus 1. Okay, so these are 13 letters. Now the problem is these are not different letters. Some of them are repeated, and they are repeated in different numbers. So look at the A repeated in 3 times, the S repeated in 4 times, N 2 times, I 2 times. So these must be excluded by the rule of division. But excluded how? We need to exclude their factorial, the number of their repetitions. So it's actually a permutation, yes. The all set is 13, so 13 factorial divided by what? Actually, not 13 minus the choices here. We don't have choices exactly the way we think. Now what we need to do is the exclusions. The exclusions is what here we have? A 3 times, so 3 factorial multiplied by 4 times for S, and also multiplied by 2 for I, multiplied by 2 for N, and that will make the final answer. And as I said, usually I don't care about this number unless we give you some other policy. I don't think for my case, I don't usually care about the final answer. If your application is good enough, that's it for me. Okay. Now let's get back to the circular arrangement. Why? Because I'm addressing the permutation, so I need to link it to the circular arrangement of the table we explained earlier. Let's think about a few things. Imagine I'm arranging 5 persons in a queue. So if we speak about a queue, we may think about the beginning and the end, so we have what we call a reference. So for the first person, I can place in any of the 5 positions or locations. And in that case, we have 5 possibilities. For the second person, we will have not 5, 5 minus 1. And for the third, we will have 5 minus 1, or 4 minus 1, and so on. I'm sorry. Okay, so that is the case, and in this actually application, it's a straightforward. Why? Because we have a reference, beginning or end, or maybe middle, but we have a reference. It doesn't look to me same. There is left and right, okay, or front and back, or rear. That is how we apply it. But for the circular representation, I explained about it earlier. The first person to be seated or to be arranged, wherever you put, looks the same to the center. And in that case, there is only one choice. Once that person is set, then okay, we have less choices. So we have 5 minus 1, 4 choices. The next one would have 4 minus 1, 3 choices, and so on. Okay, so that is the idea, and it gets us back to the rule of division, or the circular permutation. Circular permutation is exactly applied by the rule of division, or n minus 1 factorial, or if you like, n factorial over n. So these are equal actually. Mathematically they are equal. Okay. Now, the circular permutation, you can apply it, as I said, in these 2 rules, but we have also another exception. Imagine the circular permutation as just one dimension, but if we say it's a ring or a bracelet, then it is 2 dimension actually. So we have 2 places or 2 positions or 2 locations to seat a person where they look the same. So it is exactly less by half. So it's a half of the count for the circular. Why? Because exactly the half. So it's like we have a circle on top of a circle. We compose a ring in 2 dimension, or if you like 3 dimension, okay, as in our nature. So in that case, we have less by half possibilities. It's divided by half. Why? Sorry, why? We said again, we can sit one person here or down here. We're divided in half for the ring possibility. So for the ring permutation, ring, how do I know it is ring? The question will tell you if it's a ring or a bracelet or resembling a bracelet or a ring. So you will need to apply n minus 1 factorial divided by 2. Okay, and now let's just take a straightforward example. How many different ways can 12 football players be arranged in a circular huddle? Circular huddle or table is the same, so we don't have a reference. Okay, if we don't have a reference, then it is a circular permutation. 12 minus 1, that's 11 factorial, that's it. Or if you like, 12 factorial divided by 12, and that's it. That's the answer. Okay, let's take another example. Speaks about the ring. In how many ways can 8 different charms, or stones if you like, be arranged in a bracelet? Bracelet is a ring. It's not a circle. It's an object that has like 3 dimensions in this case. Okay, we don't look at it from one perspective only. Okay, so in that case, we speak about the ring. So 8 different charms, 8 minus 1, that's 7 divided by 2, why 2? Sorry, 7 factorial divided by 2 because it's a ring, so I apply the ring principle. Combination. Now we said about the permutation, the order doesn't matter, right? So, sorry, the order matters. The order matters, we said for the permutation. For the combination, the order doesn't matter. What does it mean? So when we say ABC, it is the same as BAC. What does it make? It makes fewer possibilities than the permutation. Why? Because if the order now doesn't matter, it means that we have less number of counts or less number of possibilities. Okay. Now, what is the application of combination? Don't worry, I'll give you a few examples where you can differentiate literally between permutation and combination. Okay. If the order matters, Now we have a rule for this. You can find this derivation from your textbook. I usually do not ask about it, and we are not actually obligated to go through it. However, if you are interested, you can check. For the combination, we need to exclude by the rule of division the number of repetitions. So now remember, the permutation of any subset from a whole set, so subset R taken out of the whole set n factorial divided by n minus R all factorial. Now we need to exclude one more thing, the subset, as what we did here, if you remember, for the for the counts of those. Okay, because of the repetition we need to exclude it. Also here we said the order doesn't matter, we need to exclude for the order, so we exclude what? The repetition, and this is usually the case. The combination of R taken of n, or taken from n, R subset, and n is whole set. There are different ways, by the way, for representing the combinations and permutation, but remember, it doesn't matter, the concept matters. So what you say is C n R, or C R taken of n, or you represent it by big parentheses, putting the set and the subset. It doesn't matter. What we are following for the semester is this way, and the important is the application of the rule. Okay, so we have less count. Why? We have the rule of division. In this case, we need to exclude the repetition because the order doesn't matter. Okay, so now think about this. To play a particular card game, each player is dealt 5 cards from a standard deck of 52 cards. How many different hands are possible? Now, do we have anything related to the order matters or doesn't matter? Now, do we care about the order here? For the combination, the order doesn't matter. If we hand it to the first person or the second person or the third person, as long as we hand all of them, does it really matter? It doesn't matter. There is no any rule here. So it's combination, it's not permutation, right? So we need to hand 5 cards from the total of 52, okay, each time. So that's exactly concept of combination, not permutation. So the order doesn't matter. If the order matters, yes, in that case, well, we need to apply permutation. But here it's not said, so assume that it doesn't matter. Any of them can take in advance. If we say the order matters, we go from right to left or from left to right or whatever, there is a certain reference, then in that case we have an advanced counting way. We will discuss it later on, not now. Okay, so now what we need to do is we need to just consider the combination of what? 5 taken from 52, and that's 52 factorial divided by 5 factor, we exclude the subset, and then exactly what we did with the permutation, 52 minus 5, all factorial. The final answer doesn't matter actually. The final answer, you can try to get it, to train yourself, but to me it doesn't really matter. Now let's take another example. This is more obvious than the previous example. A student must answer 3 out of 5 essay questions on a test. In how many different ways can the student select the questions? Now look at it. Does the order matter or it doesn't matter? If the order matters, then it is permutation. If the order doesn't matter, then it is combination. How do we know? Now think about it. You're a student. If you answer 1 and 3 and 5, so does it look to you as 5, 3 and 1 or not? It is. It is. Why? Because if the order here, the order of saying them doesn't change the fact that you answered 1, 3 and 5, not 5, 3 and 1 or 3, 5, 1. It doesn't matter because you answered these 3. You selected them, you answered them. So in that case, it's a combination. It's not permutation. Why? When we say, okay, you answered, let's say you answered 1, 2, 3. Or you say, I answered 2 and 1 and 3. It doesn't matter because they are still the same. Or you say I answered 3, then 2, then 1. Well, it doesn't change the fact that you just answered the first 3 of them. So that's combination. And combination, the whole set is 5, so factorial 5, or the factorial of 5, 5 factorial, divided by 3 factorial, multiplied by 5 minus 3, all factorial, and that will make you 10 options or choices available. This is the end of chapter 1. We will have a short tutorial session, like 10-20 minutes. Later on I'll upload it. Until then, have a good time. Goodbye.